No, Ant-Man's coming.
Do you agree with Ant-Man?
Whoa. Let me move so I don't get my laser eyes.
Your laser eye?
Laser
Oh, your laser eyes?
LASIK surgery right here.
Ah, got me.
See, I'm telling you.
Don't look at it, guys. I know it's really bright and shiny, but
How can you not look at it?
I don't know.
Okay, so what I'm doing right here is that on the first one, I've got a laser, and you can do the old, give that a spray with some water. So why can't you see the laser until you spray that?
Because the
Is it not there?
bounces
The laser
off.
exists.
Has something to bounce off of. It's not just air.
Yeah, so if there's nothing there, that light is just traveling through our atmosphere, okay? So it's still going through, you just can't see it because it's not bouncing off anything. So you give a little bit of a spray, kind of do the Mission Impossible thing, and you're trying to crack through the laser field, okay? So if you can't see the laser, spray it, boom, there you go. Now, so if you'll notice right here, so right here, this is the single slit. Okay, I just have one opening that this is shining through. So notice that you've got one what we call a central maximum. Okay, so that light's going through there. So one of the debates about light was whether it was particles or whether it was waves. So if you look at this, so you've got this central maximum. Then if you notice on either side, you have like a darker region on the other side. So that's where you have destructive interference. So you've got this central maximum, boom, right in the middle. Then it's going to cancel each other out. Then you have another line out here that's brighter. So, but notice that that isn't as intense because of the fact that that light is being spread out. So, if light was a particle, it's just like that video that I just showed you. You would just have one line right here in the middle because those particles would go straight through. It's particles, boom, it's like shooting marbles, and you're just going to get one line. Now, where it gets even a little bit weirder is that now I'm going to move it over to two. So now what I did is I took that aluminum foil and I cut two very narrow slits side by side. Now you kind of got to get close to see this, but what you'll see is that there's a whole bunch of very, very, very finely spaced together light and dark spaces. And again, this was proof that light is going to act as a wave. Because if it were particles, you would just see one line on either side. But because as that light comes through, it spreads out. And you get this constructive and destructive interference. So, and we'll go through the math later on how you can calculate wavelength. So, when you get a problem like this, and I'm going to do this on a couple of different scales. So, with this one, here's that piece of aluminum foil, and I had two.
Scholars Bowl and Nintendo Club.
Oh, nerds, go.
Bye.
We'll keep recording the video.
Scholars Bowl and Nintendo Club. Please go to the small gym for your pictures.
So, in this formula, there's a couple of things that you need to keep track of. One is how far apart the openings are or the sources of the speakers, which is what I'm going to show you in just a second. Okay? So that's one of the things that you need to keep track of. The other thing that you need to keep track of is the distance from the point of origin, where it comes through, to where it's being projected. Okay? So this distance is what we're going to call L. Now, as this goes through, it's a wave, right? So because of the fact that they're waves, they're only going to constructively interfere on multiples of the wavelength. So in other words, when you get that bright spot, and if you think about it, when you get like over here, one of these, the light on this side travels a smaller distance than the light that's on the right opening. Not much of a difference, but it's a difference. And so these gaps, okay, those are going to be multiples of the wavelength because that's how you're going to get constructive interference or destructive interference. So if you can measure the distance between those bright lines, what we call a bright line maximum, then you can get an idea of what that wavelength is going to be. So here's the point. Light comes through. You're going to have a source here, and in this situation, we're letting light go through. We're going to do the same thing, but we're going to use sound waves in just a second. So you need this distance, what you're going to call D.
Students, as teachers, please come to the small gym for your group pictures. Students, as teachers.
I hate
please
days like
come to
today
the
with
small
every ounce of
gym
my
for
being.
your pictures.
And then you're going to have this, and then the other thing is going to be your wavelength. Okay? Cool? Got it? Grand. Okay. So the other way that you can show this, let me go turn the lights off. And if those of you that are musically inclined, you're going to have a better chance of hearing the difference than those of us that
I don't
are.
know if I'm.
Right? So here's what I've got set up. It looks a little bit.
This is gonna hurt you.
Okay. So I'm going to turn this on. So this is the exact same as a double slit experiment that I just showed you. Okay? But we're going to be using sound waves instead. So what's going to happen is that this distance here between the two speakers, that's going to be your value of D, okay, which in this case is much, 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 much bigger than the little opening that I had in the aluminum foil that I cut with a razor blade. So this is my D. The distance to where you're going to be walking is going to be the distance of L. So, and again, some people hear this, and some people are like, you kind of get it. So here's what I want you to do. I'm going to turn that on. I want you to start over here, and no one talks, okay, because you got to be able to hear this. And what you should be able to tell as you walk over here, you should hit a region where the sound becomes noticeably softer. It won't like cancel each other completely out because you're still going to hear some background noise. But you should hit a point where the sound becomes less intense. And then when you're right here in the middle, this is when it should be the loudest, because this is where you get your maximum constructive interference. So what you should see is that the sound gets a little bit louder, it's going to get a little bit quieter, it's going to get much louder, then it's going to get a little bit quieter, and that pattern should repeat itself. So what I want you to do, and again, if you are musically inclined and have good sense of sound, those kids have the best chance to like, oh yeah, I hear that. But just start here and walk slowly across, and even you can even like stop and kind of move your head back and forth, especially when you get in the middle, because that's kind of when you'll be able to hear that. So this is the exact same thing of what I just did with the light, only it's just a much, much bigger separation. Got the idea? Okay, so I'll turn this on. Do the walk. Do the walk.
This is not.
Okay, let me try it. So yeah, so you're just going to go like this. So like right here in the middle, like I have horrible hearing and I can hear it, okay, where it gets a little bit louder and then gets softer. So that's going to be that distance. You're going to have a relative maximum in the middle. It's going to get a little bit softer, and it's going to get a little bit louder again. So try it. could set that up, and there wasn't like all the continuous background noise, you would actually hear like it go really, really loud, and then gain sort of to zero, and then get really, really loud again. But you always had that background noise too. Now, the other thing about light is that light changes speed depending upon the medium. So,
Scholars, bowl, and teens as teachers, please report to the small gym for your group pictures.
well, I need you to hold that test.
Scholars, bowl, and teens as teachers, please report to the small gym for your pictures. Thank you.
So all this is just vegetable oil. I'm going to pour this in here. Okay. So light has its maximum speed in a vacuum. So air technically isn't, we don't technically live in a vacuum, but for the most part, unless it's some really, really weird case, you can assume that the speed of light in air is just like the vacuum, 3.00 times 10 to the 8th meters per second. So if I take this and put this in here, okay, you can see the test tube, which is actually fairly complicated. So if you look at what has to happen for you to be able to see this, so light has to start on one side. It's going to travel through the Pyrex glass, and that's Pyrex has a certain what we call index of refraction, which is what we're going to get into. So index of refraction, the bigger the number is, the more light slows down in that material. Okay? So like diamonds have a very, very high index of refraction, and that's what makes diamonds glitter, is because of the fact they bend light. Okay? So it's got to go through here, go through the oil, hit the Pyrex that makes up the test tube, go through the air inside the test tube, go out the other side of the test tube, through the oil, through the Pyrex beaker, and then travel to your eye. Okay? So even if you hold this up where you can see me, right? So what color is my, and this is going to be important later on. What color, does the color of my shirt change depending upon if you're looking at through this or just normally? Does the color of my shirt change? No. Still blue, right? Okay? So what you're going to see is that the frequency of light is what determines the energy. So what that means is that if I have this, whether that light is bouncing off me and just going through air or bouncing off here and going through there, it looks the same because it's the same energy. And it's the same energy because it's the same frequency. So listen to me. Begin to plant this in your brains right now. Frequency determines color. And if the color stays the same, it's because the frequency stayed the same, because the energy stayed the same. Okay? Got that? Now, well, I need you to hold this like that. Okay? Just like that. Got it? So hold the beaker and the test tube. You got to multitask. Okay? Now, rest that down in the bottom. So what I'm going to begin to do is I'm going to begin to pour oil into the test tube. Okay? Then I want you to watch what happens with the test tube. Nope. Stay with me here. So what happened?
You can't see it anymore.
It disappeared. Test tube's gone. I made it evaporate. But if you pull it, if you lift it up, ooh, it's still there. But if you put it back down in there, it goes away. Okay? Witchcraft. Burn him at the stake. He's a wizard. Okay? So why did it appear to disappear? Why did it appear to disappear? It has to, well, kind of, it has to do with index of refraction. So the oil and the Pyrex have the exact same index of refraction. Okay? So what that means is that light is traveling through there, it doesn't speed up or slow down. Light can't tell the difference. So what allowed you to see the test tube before was the fact that air had a different index of refraction than the Pyrex and the oil did. But when I filled that up with oil, then the speed of light remained constant through that medium, and the photons are going, we can't tell any difference, we're just going to keep traveling at the same path. So this is why that appears to just hover in there and disappear, because everything in there has the same index of refraction. Got it? Good? Grand? Okay, stop that. Let's head back.